Hi, welcome. Today we are going to analyze and understand the principal component analysis for feature reduction. Principal component analysis is a technique we use it for the feature reduction in data science or in statistical analysis. It was invented by Carl Pearson in 1901. It's just a statistical process for the orthogonal transformation of one set of features to another set of features, or a vector to another form of vector. And the advantage is, for example, we have marks of quiz and the marks of midterm, and that are correlated in a data set. The PCA will result in a new set of features which are um, not non-correlated set of features or the set of components. Okay, just have an analysis of the execution or the algorithm of the PCA. It works on the computation of covariance matrix, that is the related variance of feature with respect to the other features. Then computation of the eigenvalues. Eigenvalues are a mathematical entity or the magnitude of the vectors, and then eigen sorting of the eigenvalues for the most important features. The higher the eigenvalue, the important or the most distinguished or the most useful is the feature. Then computation of the eigenvectors for first k eigenvalues or the highest k eigenvalues. That k is the user defined element that will provide how many features we are going to take. For example, if we have 100 features in original and we want to use just 30 features out of those 100, then k will be 30. The 13 highest non-zero values of eigenvalues will be used to compute 30 eigenvectors, and those eigenvectors will be set of features. First of all, covariance matrix. It's just the product of matrix. For example, m into m transpose or m transpose into m. Both are similar, but the difference is about their dimensions. So we try to use the which of those computations that result in a smaller dimensional matrix. For example, here m transpose into m will result in 3 cross 3 matrix, but the m transpose into m will result in 5 cross 5 matrix. We can use both of them, but in both of them there will be maximum 3 non-zero eigenvalues. Other two will be zeros if we use m into mt with 5 cross 5 matrix. Now the eigenvalues, as we know, the eigenvalues are the values or the scalar values which can be computed by A, the original matrix, into a vector is equal to lambda, the eigenvalue, into that vector. And by this arithmetic we can compute lambda. As we have A, we can compute lambda by using A. Okay, a simple algebraic expression or algebraic solution. Just we do move lambda v to the left hand side of the equation and then multiply an identity, and then after taking the v as common, and then as we know the v is a vector and that vector is non-zero. If the vector is non-zero, then a minus lambda I is equal to 0. That arithmetic expression can compute the value of lambda, because we have just two matrices and a scalar. Scalar is the lambda. Okay, for example, here we have an example 6145, and it's about 2 cross 2. It's easy to compute, that's why we took 2 cross 2 matrix, and the identity will be also 2 cross 2 identity. So we can compute the lambda values, which are 2 and minus 13. Okay, let's compute another example. Here an example of 3 cross 3 as we studied in the initial slide. In this example, as we have A of dimension 3 cross 3, then identity will also be 3 cross 3, and the values of lambda we can get at the end of this computation will also be 3, and 1 or 2 values can be 0 as well, but we can get maximum 3 values from this set of equations. Okay, in the first example, the lambda value was one was 2 and the other lambda value was a negative value. Okay, let's compute for the lambda value 2. Okay, as you know, ab is equal to lambda b, so we have the value of lambda, we can compute v vector, and vector v here is 1 by square root 17 and then 4 by square root 17. If you see the unit vector, the unit vector is 1 by square root 17, 4 by minus 4 by square root 17. And similarly for the other value of lambda, which was minus 13, simply we can compute the eigenvector, and the other eigenvector is 1 by square root 362 and minus 19 by square root 362. The eigenvalues, the set of eigenvalues or the new feature set for this particular example will be 1 by square root 17, 4 by square root 17, 1 by square root 362, minus 19 by square root 362. In this example, we took two features out of available two features.